So we're going to do section 5.2, and we're going to be doing it in class in 3 parts. We're going to do 5.2a, we're going to do 5.2b, and we're going to do 5.2c. This video is going to take and cover 5.2a and b, and 5.2c, which is focusing on graphing. That's going to be a second video. Okay, so we're going to focus on 5.2a and b, and what we're doing in 5.2 is learning about logarithmic functions, how they relate to exponential functions. We're going to learn how to write them. We're going to learn how to go back and forth from them. We're going to learn how to solve equations with them, and then we're going to learn to graph them. Okay, so again, this is going to focus on parts A and B. In this section, we're going to learn about logs. And what logs are is really they're the inverses of exponents. When we're doing math, we learn that, for example, addition and subtraction are inverses. They undo each other. And multiplication and division are inverses, and they undo each other. We learn about square roots and squares. They undo each other. And so logarithms and exponents undo each other as well. They are definitely inverses of each other, and we could go back and forth from one form to the other. So I'm going to give you this problem. This is an exponential function, but let me give it to you as a math problem, right? Let me do, for example, 3 to the second power equals 9. And so you notice that your base in the example is a, and here it's 3. My exponent here is, this is my base, this is my exponent, and this is my solution kind of, right? The value of it. So base, exponent, and solution. And so we know that our base of 3 raised to the second power, or exponent of 2, equals 9. Well, I can write this as a log. And how we do with the log is we write the word log, short for logarithm, and we put whatever our base is becomes a subscript here, okay? Whatever our solution is, that becomes the number next to the base, and then equals, and it always equals the exponent amount. So log base 3 of 9 equals 2. Now, this is kind of weird to see. What I do is I kind of read it as, make sure that I'm right, 3 to the second power equals 9. And I know that if that little cycle works, I wrote it the correct way. So again, you notice if I did letters, my base was A, so my base is down here. So it's going to be log to some base. I'm going to have my solution here, and I'm going to have my exponent there. And those are my 3 spots. So what we're going to do is kind of focus on going from logarithmic form to exponential and back. So here, the first 3 questions I'm given in logarithmic form, and I have to convert to exponential. Remember that little curve I told you? The base to the exponent equals the solution. So 2 to the third power equals 8. So I find this to be the easiest one to do. So this is a base of a half to the negative 4 power equals 16, like that, okay? And again, check yourself. Half to the negative 4th power is the same as 2 to the 4th, and 2 to the 4th is 16, and it works. So again, my base to this exponent equals this solution. 10 to the 5th power equals 100,000. Yes, it does. So these are how you go from logarithmic function to an exponential function. And if I'm doing it the other way, I'm going from an exponent to a log, right? I know I have to have the word log in all of these. And I know that this base becomes my subscript, this solution goes here, and my exponent becomes the answer on the other side. And so I'm like, okay, let's double check it. 5 squared is 25. I definitely did it right. Okay. So again, I come to the next one. I know that my base becomes the subscript there. My solution on this other side goes here, and my exponent goes on the opposite. So in a log, what you're in essence doing is solving for the exponent, oftentimes. And again, 3 to the negative 4 power is 1 over 81. So again, I know I did it correctly. Anyway, here my base is 3/4. 1 is my solution, and 0 is my exponent. So that's how I write it. And again, 3/4 to the 0 power is 1. Anything to the 0 power is 1. And so that's how we go from logarithmic to exponential and exponential back to logarithmic. So in this video, I'm going to do part 1 and part 2. So I'm going to go over, even though in class in part 1, I only went over number 1, I'm going to do them all. So properties of log. So the first one is anytime you have log base A of 1, it's going to equal 0. And if you think about it, it makes sense because think about when I write that, that's a to the 0 power equals 1. Anything to the 0 power is going to be 1. The second one says log base A of A equals 1. So what happens is, again, think about what we're saying here. We're saying that A to the first power equals itself, right? And so that makes sense too. Anything to the first power is going to equal itself. And so when you see something like this, base A and then the value is A, it's going to equal 1. And then if we go to number 3, you're going to notice, again, same thing. It says log base A of A to the x power equals x. Well, again, when you have this base and this, these two cancel, and it's going to leave just the exponent at the top, okay, as your answer. So again, if you think of the one above it like that, log base A of A is going to equal what this exponent is. Now again, you can see that it's true the long way, but eventually you're going to want to just be able to see it, recognize it, and know the answer to this one is x. Because again, you've got, think of it like this, A to the x equals A to the x, and that's true. And then the last one says if log base A of x equals log base A of y, then x and y must be equal. And that's true too, because again, log A and log A are exactly the same, so that if they're equal to each other, it means the x and the y also have to be equal. But for that to happen, the bases have to be the same. So let's do a bunch of problems and solve, these equations with logs and see how it all works out. So a lot of those properties are not going to be utilized in these first several problems. Here, we're just solving. So again, here we have a base of 2 raised to the x power equals 32. Now, a lot of you at this point already know that 2 to the 5th power is 32. So x must be 5. Now, if I was going to do this the longer way, maybe even the most appropriate way, I would make their bases the same. Once the bases are the same, I can cancel them and make my exponents equal to each other. I go to the second one and I go from logarithmic to exponential. My base is 4, my exponent is x, and my solution is 2. So 4 to some power is 2. For all of you that are really good with these kind of exponents, you know that the square root of 4 is 2, and so the square root is the same as the 1/2 power. So I know x is a half, but to do this a little bit better, maybe I'll do 2 squared to the x power equals 2 to the 1 power, and then I know this is 2 to the 2x power equals 2 to the 1. Now that I have the base the same, 2x equals 1, and x equals a half. Okay. Here, again, I have log base 3 of 1 equals x. So again, 3 to the x equals 1. And I know that means that x is 0. Remember that anytime you have a log with a base and the value there is 1, you know that the other side of the equation is 0. So we keep going again. We have 10 to the x power equals 1 over 100. 1 over 100 can be written as 10 to the negative 2 power, and that way my base is the same, and I get that x is negative 2. Again, this is going to be x is 0 because 6 to the x equals 1, which means x has to be 0. Anything to the 0 power is 1. And then I go to this last one here, and I do 5 to the x power equals 1 over 125. So 5 to the x power equals 5 to the negative 3 power, which means x is negative 3. So here's a bunch more problems kind of the same skill. Again, I have 7 to the x power equals 343. I'm going to change the base here. I know 343 is 7 cubed, so x is 3. Now 14 is a little bit different. 14 is x cubed equals 8 over 27. And so here I have to think about this. Here I'm not given the exponent as my variable, but my base is my variable. So I have to try to see if I can convert 8 over 27 to something cubed. And I know I can, because I know 8 is 2 cubed and 27 is 3 cubed. So 8 over 27 is the same as 2/3 to the third power. If my exponents are the same, then I know my bases are equal, and x is 2/3. I go to the next one. It says basically 4 to the 5/2 power equals x. So here I just have to basically solve. I know 4 to the 5/2 power is the square root, the second root of 4 raised to the 5th power. Well, the square root of 4 is 2, and 2 to the 5th is 32. Okay, and so I know x is 32. Again, keep going. 49 to the x power equals the cube root of 7. So let's think about this. 49 is 7 squared to the x power, and this is 7 to the 1/3 power. So this is going to be 7 to the 2x equals 7 to the 1/3. My bases are the same, so 2x equals 1/3. I'm going to multiply by a half, and I'm going to get that x equals 1/6. So again, you have to know how to work for fractions and square roots. We've got 5 to the x power equals 1 over 625. 5 to the x equals 5 to the -4 power. So x is -4. Some are very basic, and then some are so complex, right? When you have decimals, I suggest you write them as fractions. So this will be 10 to the x equals, right now it's 0.001. So 10 to the x equals, and I'll write this as 1 over 1,000. That helps make it clear that 1 over 1,000 is 10 to the -3 power. And that helps me to identify that x is -3. And now we start getting to some of these properties, okay? So what this one says is x equals, and I like to put the equal sign over here. I like it to look like that. But basically 8 to the x equals the 4th root of 8. So 8 to the x equals 8 to the 1/4 power, and that means x is 1/4. Now here, this one's kind of weird, right? So we've got, this is a little bit different. And I didn't see this property there yet the other day, or, you know, up, not the other day, but above. It says that if I have the number 3 raised to the exponent log 3 of 8, right, it equals x. So let's do it like that, right? So when I get to this problem, there's a couple ways to do this. I just didn't think that we had learned how to do this, but basically there is a property that says that if you have a base and it's raised to log base 3 of 8 like that, if the base and this base match, these cancel, leaving just the number that's left over, and that's actually the answer. Now, how would I do this in a little bit different way? You have to think about, if I take, this is really an exponential function, and if I was to do this, remember the exponential function would be log. This base would go here, right? This solution would go there, and on the other side would be my exponent. And so if you notice, if I write this exponential function as a logarithmic function, notice it says log base 3 of x equals log base 3 of 8. These cancel, leaving me with x equals 8. So there's a valid explanation for it. It's just that you're going to want to just do it from here. Again, if I have, 4 to the log base 4 of x power. This and this cancel, leaving my answer as just x, just whatever's left over. Same goes here. So if you notice here, I've got 2 and then raised to the log 2 power. So x equals 9. The 2 log 2 cancels. Over here, I have x to the negative 2 power equals 25. So let's think about that. So x to the negative 2 power, and over here, I know that 25 is 5 to the positive 2 power, right? So how can I make it a negative 2 power? Let's see, x to the negative 2 power. And I could do this 1 over 5 to the negative 2 power. And so I know that x equals 1/5. This one's a little bit tough. Again here, I know 4 to the 3rd power equals x. And so 4 to the 3rd is 64. So 64 equals x. And last one, again, I like to do it like that, but I get 4 to some x power equals the cube root of 16. And I've got 4 to the x power equals 16 to the 1/3 power. Now, I know that 16 is 4 squared. So 4 squared to the 1/3 power. Remember, I want the bases the same. So 4 to the x equals 4, and I'll do 2 times 1/3, 2/3. So x must be 2/3. What we're going to do here too is, before we get to the graphing, which is on the next few slides, we're going to go and talk about natural log slide, and then we're also going to solve some problems with natural log, which is E. So we're going to, again, skip ahead a few slides. We're going to skip the graph. The graph will be in part C. So in this slide on natural log, I want to talk about natural log, but I also want to talk about something called common log. And so in the problems we've been doing, for example, log base 8, we've been doing problems log base 4, we've been doing problems log base 10, whatever the base was. We've even done problems log base E. And so the two that I want to talk about are log base 10 and log base E, okay? Log base E is what we're going to talk about in this slide, and what that's called is the natural log, because the base is the natural number E that we've talked about before, that E has a value, E is approximately equal to 2.71, and it keeps going. And so when E is your base, we call it natural log, and we can either write it as log base E, or we call it ln, natural log. So again, either one means the same thing. It's just a different way of writing it. And log base 10, this is called a common log. And what that means is that whenever you look at your calculator and you see the word log, know that the base is 10. So when the base is 10, sometimes we'll do like, log 1 equals 0 or something like that, and you don't see a base here. Well, when you don't see a base, it's 10, okay? That is going to be the default. So log base 10 is the default. When you don't see a base, it's 10. You know that it's 10. I'm telling you that it's 10, and it's known as the common log. So now that we differentiated between common log and natural log, we're going to talk about natural log. And all the properties that we applied to common logs and normal log problems, like all the other properties we discussed, are going to apply here. So if I write something like log E of x, I could also write it as ln of x. These equal the same thing. Okay, so again, I can write log base E, or I can write ln for short. Again, it has all the same qualities of other logs. So in other words, when you see a problem that says the natural log of 1, it always equals 0. Now, let's see how we can prove that the natural log of 1 equals 0. Well, if I change that to log base E of 1 equals 0, let's think about that. E to the 0 power equals 1. Anything to the 0 power equals 1. So any question like this, including natural logs, is going to equal 0. So again, if I have log base 3 of 1, that equals 0, because 3 to the 0 is 1. If I have log base 10 of 1, that also equals 0. If I just write log 1, it equals 0, because I know this is a 10, and 10 to the 0 power is 1. And again, if I have log base e and it of 1, I know that it has to equal 0. So this, again, is a property that we're going to apply to all logs, including natural. Okay? The second one says this, that the natural log of e equals 1. Well, let's think about that. The natural log of e is log base e of e equals 1. Well, let's write this out. E to the 1 power equals e to the 1 power. Remember, this is like to the 1 power. And so, yeah, I see that if I write it out, it's true. And this works for anything, not just log base e. If I do, log base 10 of 10, that also equals 1, because 10 to the 1 equals 10. When this base, and that one I wrote it kind of big, right? But when the base, like here, equals this, the answer is going to be whatever this exponent is there. In this case, since the exponent is 1, it equals 1. In this next problem, since the exponent is x, it's going to equal x. And that's another property that you want to learn. So again, let's do that second one. Log base e of e to the x power equals x. When you have the base and this number and they match, they cancel out and the answer becomes that exponent there. And that works for anything. So if I have log base 3 of 3 to the 4th power, I know that this is going to equal 4. It's going to equal this number. The base and the of part, if these match, they cancel. Okay, and so again, another property that you want to learn to recognize so you don't have to write it out the long way. Okay, and the last one again says that if the natural log of x equals the natural log of y, then x equals y. Yeah, because you'd cancel the natural log part and you'd be left with x and y. So again, if I expanded this out, log e of x equals log base e of y. And yes, everything else is the same, so the x has to equal the y. So now let's solve a bunch of problems and actually apply it so you can see it in practice. So for these, obviously I'm going to switch them over to log base e type. I'm going to rewrite them, and if any properties apply, I'm going to apply them. So in this one, I know that ln of 1 over e is log base e of 1 over e equals x. Now, when I rewrite this as an exponential function, I know it means e to the x power equals 1 over e. Well, 1 over e I know is e to the negative 1 power, and I can cancel the base, and I get left with the fact that x equals negative 1. Now, when I come over to this problem, this is another property that I'm not sure that we've discussed yet. And again, notice that when I rewrite this, okay, it equals e to the log base e of 5. And when I have the base here and it's raised to the log e power, this is like an exponential function. But when the exponent is a log with the same base, I can cancel it and x just equals 5. Now, if you want to do it the long way, since this is an exponential function, right, I'm going to actually make the x over there. This is an exponential function that says e log e of 5 equals x. And I know that to convert an exponential function to a logarithmic function, this base now becomes the e, right? This solution goes here, and it equals the exponent, which in this case is log e of 5. And notice that log e and log e match, so x equals 5. Now, I don't think you want to do it the long way every time. It's good to see it so you can prove it to yourself. But again, you just know those e and log e, or natural log, cancel, leaving you with just 5. Again, when you come over to this one, you could do it the long way, or you can remember the patterns. Remember that we talked about, right, this is 2 times log base e of e. And we learned that when you have log base e of e, it's kind of like e to the 1. This cancels, leaving you with just the 1. And so x equals 2. Okay, so that's, again, one of the properties on that other page. Again, I go to this one, and I have log base e of e to the 1/3 power equals x. And again, log base e and e cancel, and x equals 1/3. When I come to the next one, I have 5 times the natural log of 1 equals x. Well, remember that this is the same as log base e1, but we already talked about that, and anytime any log to any base equals +1, we know that that whole thing equals 0. Oh, so I know that x equals 0. And the last one is 3/4 times, again, log base e of e to the first power, right? This I know equals 1, so 3/4 times 1 equals x, or x is 3/4. And the last one, again, is another one of the properties. Again, that's log base e of 7. And when I have a base and an exponent with the same base, they cancel, and I just get that x is 7. So, of course, the better you get with the properties and recognizing them, the quicker you can solve the problems. Yes, you can do them the long way, you can set them up, but those shortcuts, if you can identify them and you can remember, again, that ln of e is always going to equal 1. If you can remember that ln of 1 is always equal to 0, then those are going to be really easy for you to solve when you find them.